So we talked about yesterday with graphs, or I introduced graphs today or yesterday, and there's a piece of that that's really important that I want to emphasize, and that is how looking at graph motion or how something moves with respect to time gives us a lot of information, because there is information there on the slope of the lines, and there's information there looking at the area under. And one of the things I encourage my students to do when we're in person is on exam day make 3 quick graphs. And that's what I have drawn on the tablet here, is 3 quick graphs in terms of acceleration, in terms of position, and in terms of velocity. So let's go ahead and label some axes here. So I'll go over here. This first one I'm going to do as velocity, and remember that has units of meters per second. And then I'm going to do time in terms of seconds on each x-axis. So the next one over, let's go ahead and make that, let's see, acceleration. And that will be in terms of meters per second squared for its units. And then once again, in terms of seconds for time. And then the third graph, number 3, let's go ahead and make it position. So it's position in terms of meters. And then on its x-axis is again going to be time in terms of seconds. So there's a quick thing I want to remind you of for being able to keep everything straight as far as integrals and derivatives go. And that's if I look at the slope of the line, here's my slope. Remember, that's defined in terms of rise over run. Rise over run. Another way to think of that is that the change in my y-axes, because these are all going to be our standards. So if I look at this, I'm going to have x going that way and y going that way for just standard axes. So the change in my y is my rise, and the change in my x is my run. So let's take a look at that for velocity. What do I get? For velocity, let's see. Velocity. I have a slope of my v final, my final velocity, minus my initial velocity. And that's going to be divided by the amount of time that change took. Let's do that in terms of our units then. On the top, velocity minus velocity, that's just meters per second. That's still just velocity. And on the bottom, I have units of just seconds. So that gives me units of meters per second squared, otherwise known as acceleration. Cool. So what does this tell me? If I look at the slope, if I look at the gradient of a line, I'm actually looking at the derivative. The derivative. So the derivative of a function, of a velocity function, I should be very specific there, is going to give me the acceleration. And that should make sense. It's how the velocity changes with respect to time, and that is acceleration. If I have no change, I have no acceleration. I'm constant velocity. So let's do that with acceleration then. So for acceleration, I have, let's see, let's just jump right to our units. I have meters per second squared divided by seconds, and that's not feeling very familiar. I'm going to rewrite that in terms of meters per seconds cubed. And that actually is something. So if acceleration is changing, we call that the jerk. That just means acceleration is changing. So think of it as if you're slowing down at a constant rate, so you have constant acceleration in the car, and then you hit your brakes really hard, so you've changed your acceleration. You get kind of like this jerky motion that happens. That is called the jerk. Now that's not something other than playing around with looking at integrals and derivatives. As the only time you're actually going to see that as far as something that we physically analyze. That isn't something that we'll be doing in this class. So math, yes. physically studying it? No. So that's the derivative of velocity and acceleration gives me, I'm sorry, velocity gives me acceleration, and the derivative of acceleration gives me the jerk. And now let's look at displacement. Displacement. Let's see. So my units there is going to be meters for going in the x is my meters, and my y is in seconds, so meters per second. So the derivative of position of a position function will give me velocity. Now the last step, so we have a derivative. What we haven't done is looked at what the integral would be. So an integral, let's just kind of write it over here. You can think in terms of what does that shape look like? Well, it looks like that. And that's actually shape of an S for a sum. So what's an integral doing? It's summing up teeny tiny little slivers under each of these curves. It's adding up the area that we're interested in. Little tiny pieces with respect to time tell us something about what is physically happening in a system. So if I look at this graph, well, all of them are, I made triangles. If I look at this, well, that's a triangle, so the area under the curve, is my integral, is the integral. And in this particular case, if I wanted to actually calculate something, I can remind myself that the area under a triangle is 1/2 base times height. So again, let's try this with each of them. So for velocity, what do I get? I get 1/2 base times height, so meters per second. Ooh, that's a second. There we go. Times seconds. Well, that gives me displacement. So integrating that is not a word that I just wrote. Displacement. There we go. So integrating the area under a velocity curve, like that gives me the displacement. If I integrate it, I get the displacement. If I integrate acceleration, come on, here is in my face. If I integrate acceleration, I have meters per second squared times seconds. Well, one of those seconds cancels out, and that gives me velocity. So the integral of an acceleration function is velocity. Pretty cool. I can come to x, and I look at that, and I'm like, wait, there is nothing underneath x, that's just meters, so it's just displacement times seconds. And I think for now, we're just not going to worry about that. We'll just be like, nothing. Nothing. We'll talk later how we can capitalize on some of the position with the integrals. Okay, so there you have it. Now, you don't need to have this long conversation with yourself about what all these things mean. But if you just quickly write down your units, if I come over here and if I go meters per second divided by seconds, so the slope on this is meters per second squared. And then I remind myself that I'll have here meters per second times seconds. So this area under the curve is meters. And I can do that real quick on all of them. I never have to guess or try to memorize what any of my integrals or derivatives do for any of those functions. I can think in terms of what is actually being physically analyzed, and I'm going to get it right every time.